Valsalva wave. It is derived from the whole Valsalva wave by measuring the blood volume at the interbeat interval at the cardiac diastole, each one of these small valleys. That is measured and plotted, which then forms the fast Valsalva wave. There is a slight delay you can see here between processing associated with that and the fast Valsalva wave. Some of this is due to the Camtasia recording that I'm doing now, which puts a large real-time burden on my PC, even though it's pretty high powered. I don't think you'll see that difference when you use it. I don't usually see that difference, so I wouldn't expect that to happen. Below that is the AC pulse wave. This is derived from the top edge of the whole Valsalva wave. You can see that they map very directly with each other. The AC pulse wave is an AC filtered version of the whole Valsalva wave, which basically takes off the relatively high frequency AC variation as a function of heart rate and plots it here as a line graph centered around an x-axis of 0. You can see the x-axis is this center line right along here. Heart rate is measured or derived from the pulse wave by measuring the time between the rising edge of each consecutive pulse wave. So right here is a rise interval. The rising edge of this pulse wave to the rising edge of this pulse wave. We take that time, divide that into 60, and plot it down below as a real-time measure of heart rate in beats per minute. That is how heart rate is normally computed in the great scheme of things. Over to the left we have a brief explanation of each of these biometrics: whole Valsalva wave, fast Valsalva wave, AC pulse wave, and the heart rate. Depending on your screen size, you may need to scroll down to view this. This gives you a brief explanation of each one. And again, all other signals under Valsalva wave menu, heart rate menu, pulse wave menu, and simultaneous signals are ultimately derived from one of these. When you hook up a sensor to a human being, I recommend that you come to basic signals. Let's get started option 3 and confirm that you see signals like this. You see a good whole Valsalva wave. That is, you can see the heart rate is clearly present. You can see a more slow underlying rhythm, having to do again with respiration and autonomic governance of vascular activity and blood flow. And you can see a good pulse wave. This pulse wave looks real good. From this we can easily derive an accurate heart rate variability measure. If the pulse wave happens to look ragged or erratic, then it typically means that the sensor is not applied to the body snugly enough. This being said, the general goal is to apply the sensor as loosely as possible while picking up the whole Valsalva wave and the AC pulse wave. You will see in your use of this instrument, there will be times when you get a good pickup of the whole Valsalva wave, yet the AC pulse wave is not does not have integrity. Tighten up the sensor just a bit by placing it a little differently, tightening up the elastic band on the finger just slightly, or the same on the ear. Now, before we leave this panel, I want to demonstrate one of the controls on the left-hand side, or actually all of them now. We'll use this opportunity. That is the magnifying glass. So if I want to select whole Valsalva wave and then shift to full screen view, I click on the magnifying glass, and now I have a full screen view of the whole Valsalva wave, which I can use for monitoring purposes or certainly for biofeedback purposes. I'm able to control the rate of this screen with these two arrows. I can make this much faster by clicking the long arrow. Here you see we now have a 10-second screen with more resolution. So if you're looking for good resolution, very high resolution of something, you can get that by clicking the long arrow. Or the short arrow to shorten things up again. Hello. We just auto-gained back into a state of reason. I've been waiting for that. So you can use the long and the short arrow to speed up or slow down the screen depending on what you'd like to see. Of course, a biofeedback session, we have to choose these things correctly. It's important in the beginning that clients are able to see that their actions affect their biometrics in real time. So we want a relatively fast screen when people are just learning. But after they have good control and a solid understanding of how to do this, then we could go for a much longer screen. Maybe one that even extends over a period of 20 minutes, like this one. The fast Valsalva wave is not a good example of this kind of screen and its usefulness, but a line graph would be. Above that, we have the ability to turn auto gain on and off. Most of the screens are enabled to auto gain programmatically, and they will do that automatically in order to maximize the amplitude of the graph while fitting it on the screen. But this can be a little distracting at times, depending on what you're measuring and what the goal is. We can turn off the auto gain by simply clicking this, in which case now, if the metric varies above or below the upper or lower bounds of the screen, it will not auto gain. It will continue to fit the image on the screen that we're watching. We'll turn that back on. Above that is to lower the gain. If we would like to scrunch the signal down, you see that? We're lowering the gain. Or raise the gain back up. I'll lower it back down slightly. Here we can shift the curve downward on the graph or upward on the graph, on the graph matrix. All right, that makes sense to everyone? There's some other controls here having to do with thresholding and feedback that are not enabled yet, and I plan that they will be in first quarter 2010. A software update will be made available to you at that time to begin to use audible feedback and thresholding on certain of these screens. We're going to go ahead and leave off here to prevent the file size of this recording from becoming too unwieldy. We'll pick up where we leave off in the next recording. I'll see you then.